world is full of specifications, thousands of pages of engineering specs, and test procedures that manufacturers have to go through. So our job really is to ensure that Bluetooth is the same on all devices and therefore interoperable. That's what the standardization process is all about. So I was involved in the webinar series a few weeks ago and gave another talk, and I selected a number of basically unrelated topics to look at very closely in that last talk, which you may or may not have attended. Today I'm going to talk specifically about Bluetooth Mesh, and I'm going to take the perspective of the Android developer ultimately, but I'm going to start off by introducing you to Bluetooth Mesh, which not everybody knows about. It's a new subject to lots of people, and hopefully, you know, by the end of this talk, you'll know what Bluetooth Mesh is. You'll understand some of the key things about how it works and the sort of terminology that's involved. Because obviously, there's lots of terminology. Wouldn't be a good technology with lots of new terminology for us to get our heads around. And you'll also understand what the opportunity is for smartphone developers and what's involved in creating Android applications that work with Bluetooth Mesh networks. So I'm going to start here, which is a slide I very typically use because the word Bluetooth means many different things now. In the beginning, and I'm talking 21 years ago now, Bluetooth was released, and specifically that's a Bluetooth technology we call Bluetooth BR EDR. That stands for Basic Rate Enhanced Data Rate. That's the original Bluetooth. It was really a cable replacement wireless technology, and it lets two devices communicate directly with nothing in between, and still very much used in the world of audio. So something like 1 billion devices ship every year in the wireless audio market, so wireless headphones and so on. And they use this older sort of Bluetooth BR EDR to form point-to-point connections between headphones and smartphones, say, and to stream audio across that wireless link. Bluetooth Low Energy is newer. It's about 10 years old, 11 years old now, and that's really where all the action is, where all the development and innovation's taking place. And it too can form point-to-point connections. It uses less power than BR EDR, hence the low energy name. But it can also do something called broadcasting, which means that one device can communicate data with potentially actually in an unlimited number of devices that just have to be in range and listening. And the kind of contact tracing, COVID-19 contact tracing applications that have been popping up around the world on the whole are leveraging this capability, where a smartphone is broadcasting something which other devices are kind of listening to and taking note of. So that's quite a powerful capability of Bluetooth Low Energy. But it can also do the point-to-point, one-to-one connection stuff as well. Bluetooth Mesh is quite different to all of those things. It actually uses Bluetooth Low Energy for radio communications, kind of low down in the stack, but it lets you form quite large networks. 32,767 devices is the maximum number of smart devices you can have in a Bluetooth Mesh network, but is very much about networking. And it was designed in the first instance for things like smart buildings, where things like automation are quite important, and in some cases actually mandatory with respect to kind of legal regulations that might apply to buildings in various countries, lots of which are sort of to do with reduced energy consumption and, you know, green credentials for buildings. Hard to do those sorts of things to reduce the energy consumption of a building without sensors and automation kind of making sure that everything is optimized. So Bluetooth Mesh was designed for that kind of scenario, amongst others, in the first instance. So let's get technical and start here. The Bluetooth stack isn't a single monolithic thing. You can think of it as being modular. So what you have depicted on screen is the Bluetooth stack as it exists on an Android smartphone and many other types of device as well. So at the bottom in green, we have a radio. That's a piece of hardware, a radio transmitter receiver. And then the Bluetooth stack itself is divided into two major kind of architectural building blocks. At the bottom in gray, you've got the Bluetooth controller. It has a number of layers in it, and I've shown the two most important ones there. The physical layer is concerned with using the radio and encoding digital information in an analog form that can be transmitted over radio. And the link layer is about different ways of getting Bluetooth to communicate with other devices, different states devices can be in. There's a state machine defined down there as well, quite low level stuff. And it's how digital packets get formed. And then the host in the blue box at the top has all the higher layers of the stack. There's an interface between the host and the controller called the host controller interface, and that defines commands and events that flow between those two major components. These two components, by the way, might be physically separate, might be the host is pure software, the controller might be implemented in a chip, maybe communication between the two is by USB or something else along those lines. But the host controller interface covers both aspects of that, a kind of logical interface in terms of commands and events, and physical interface requirements, such as whether to use UART or USB or some other hardware-based communication approach. Sitting in the host, though, are layers of the Bluetooth Low Energy stack, which some at least are quite visible to you via APIs. So we have GAP, which is the generic access profile. That's concerned with discovering devices and then connecting to them. GATT defines some procedures for interacting with data on the remote device in something called an attribute table. And the attribute protocol is how the two devices have a conversation about that data. Security manager protocols about security stuff, of course, and the rather lengthily named logical link control and adaptation protocol, or L2CAP for short, does things like segmentation and reassembly of large packets, protocol multiplexing, and flow control. So if you have any background at all in the world of protocols, you should recognize those terms. They're very common in all sorts of different protocol stacks. Bluetooth Mesh, on the other hand, has a host which is quite different. It uses the Bluetooth Low Energy controller, so all the sort of low-level wireless communication stuff is Bluetooth Low Energy as used in all cases. But the host is completely different, with a whole series of layers that are specifically to do with creating networks and communicating within networks. And as I'm sure you'll appreciate, protocol stacks are layered because of separation of responsibility. That's a kind of fairly fundamental architectural principle, design principle that we bring to bear in a lot of the work that we all do in designing software and systems. So various things are taken care of by those different layers. Two aspects of security are taken care of by the upper transport layer and the network layer. The bearer layer offers a couple of different ways in which the Bluetooth Low Energy controller can be used to transport mesh messages. The access layer is concerned with message types that are more to do with the application layer, and then specific application behaviors kind of different types of product are defined in things that we call models. You don't have any of this on an Android device, but there are still ways in which Android applications can be part of a Bluetooth mesh network. So that's really what we're going to be exploring in this talk. So let's start with some basics of Bluetooth mesh, and I'll start you off with some kind of network level concepts. So you can imagine a mesh network of any sort, Bluetooth or otherwise, has lots of member devices. We call them nodes. Communication is, in theory, feasible between any member of the network. And one of the things that differentiates mesh networking with Bluetooth to other ways of using Bluetooth is that you're not limited by the range of the radio. So under other circumstances, two Bluetooth devices can only communicate if they are in range of each other. Obviously, the further away one device gets from another, the weaker the signal gets, and eventually you are considered to be out of range. A mesh network doesn't work quite like that. A device that wants to communicate with one or more other devices somewhere in the network, and they may be quite some distance away in a very large building or maybe even in another building, will send a message. And that message will find its way to its destinations by hopping across the network from device to device to device. Now, we allow up to 127 hops to be done, and the range that a single hop can cover is probably in the order of over 100 meters. Bluetooth Low Energy today has a range of certainly hundreds of meters. In the context of a building, it will be less. devices that are immediately adjacent to each other need to be in range, but after that, the hopping process takes messages right across the network. So you can imagine these messages traveling at approximately the speed of sound, so latency is quite low. And the net of all this is that a mesh network, thanks to this multi-hop delivery capability, can span a very, very large area indeed. You can imagine whole neighborhoods having a Bluetooth mesh network in them. And in fact, I've talked to people who are doing exactly that kind of thing. So that's multi-hop delivery. Now, the way hopping works, though, just to be clear about this, the devices in a Bluetooth mesh network will be all sorts of different types of products. So in a smart building example, there'll be lots of lights that are mesh nodes. There'll be switches, there'll be dimmer controls, there'll be thermostats, there'll be air conditioning units, there'll be sensors, light sensors, for example, and occupancy sensors that tell you if somebody's in a room or not. And whatever the product type, there are 4 special roles from a networking point of view that any node can, in theory, take on, because they're all implemented in software and they're all enabled or disabled through configuration. So I could choose to have one of the lights in my room configured to act as a relay. A relay is one of the special roles that a device can have. And any device that's a relay will simply rebroadcast, repeat, any message that it hears from one of its neighbors. And so one of the things that makes using Bluetooth Mesh different to using Bluetooth in other ways is that there is a network design requirement. We don't tend to think too much in terms of network design when we're dealing with connectable Bluetooth low energy devices where they're forming point-to-point, one-to-one connections between two. There's not much else to think about in that respect. But with a large mesh network, I'm very much going to be thinking about which of the devices in my network need to have the relay capability enabled and where I'm going to place them. And with a bit of thought and some testing, I'll make sure that messages can hop all the way across my network to wherever they need to be. Now, from an efficiency point of view, I can send messages from a device and I can limit how far they go. I can say, don't go more than 2 hops, because if my device that's sending messages is a light switch, for example, and I know that all of the lights on this floor of the building are within 2 hops of my light switch, then there's no reason for me to want that message to travel any further. There's no point using the radio resource on the top floor of the building when none of the lights that I want to control from that switch are there. So I have some control over how much hopping takes place, but the potential is for messages to go a really long way, and so we can have very large mesh networks. Multipath is concerned with reliability. So one of the issues that I need to safeguard against when I'm designing my network is the possibility that a path across which a message might need to hop to get to its destination becomes unavailable, broken in some way, or maybe a device gets moved or it's been temporarily switched off or something like this. So again, as a network designer, I'm going to place my relays such that most of the time there will be more than one relay in range of key devices. And the effect that this has is that when my device transmits a message, let's say 2 relays will hear that message and repeat it, and so on across the network via all the devices I've selected to be relays. And what this does is it gives me more than one path that copies of a message will travel along to the remote destination. And in normal circumstances, all of those copies will arrive at the destination, and the first to get there will be acted upon, and all the other duplicates that have taken different paths and arrived slightly later will be disregarded, they'll be ignored. But this is a way of creating redundancy in your network design. If something fails, it doesn't matter because your message will get there some other way. It's a fairly simple architectural principle. One last comment on relays. It might be tempting for your first network to switch on the relay feature of every single node. Everything can act as a relay. That might sound like a great idea. But obviously relays generate traffic. They repeat every message that they hear. And so there's a kind of trade-off here between creating that redundancy and reliability that you want through having multi-hop, multi-path communication, and saturating your own network through going a little bit over the top with enabling too many relays. So you probably only want about 5% of the nodes in your network to be configured as relays or something like that. Multicast is the last of my multis on this slide. Almost all of the communication that you'll do, or that devices do in a Bluetooth mesh network, is of the multicast type. In other words, a single message addresses and is ultimately delivered to more than one device. The whole system really is designed around multicast communication, as opposed to you perhaps having to do a whole sequence of unicast communication, talking to a collection of individual devices one at a time. You send one message, and the way the addressing and message delivery scheme works, that's all it takes to get to all of the appropriate devices that need to receive that message. And the big advantage of a multicast messaging system in wireless communications here is scalability, because I can occupy a radio frequency for 20 milliseconds to transmit one message, which will cause some form of reaction, a response, from potentially hundreds of devices all in one go, as opposed to sending 100 separate messages, if you see what I mean. So multicast gives us immense scalability, very efficient use of radio spectrum, and radio spectrum is a precious resource. So let's move on from those high-level kind of network concepts and talk about how devices actually talk to each other. So first of all, as I've already mentioned, communication involves messages. The whole system is message oriented, and in many ways I think is much easier, in fact, to understand than working with other forms of Bluetooth, because the kind of concepts and the terminology are strangely familiar. We're not the first technology to decide that messages are a useful construct. So nodes in your network, products that are part of your Bluetooth mesh network, have inside them a series of what we call state. These are data items that have a particular type, and the values that they have are all defined in a specification, and the kind of transitions between different state values are defined, and the way that the device type should respond to those changes is defined. Everything's in various specifications. And Bluetooth mesh messages act upon state. So there are message types associated with each state type. And broadly speaking, there are 4 types of message that you might associate with a state, and they're there on the slide. There are set messages, which I can send to change a state value in one or more target devices. There's a GET message type, which I can send, and that will return to me the current value of a given state value in another device or collection of devices. Status messages report the value of a current state. If I send a GET message, in fact, what I get back is a series of status messages. There are actually 2 subtypes of the set message. I can send a set message which will change a state value and ask for an acknowledgement, or I can send a set message which will change a particular state value and not get an acknowledgement. Now, you might assume that acknowledgements are where it's at. It's very common in communications protocols to have requests and responses. The responses are the acknowledgements, of course. But in mesh networking, that approach just doesn't scale, especially if you don't receive a response. You have to wait a certain time. If you don't get it, you get a timeout. What do? You resend your original message. This is a multicast system, remember. One of my messages may well be addressing 100 devices. For me to be able to even track timeouts, which devices did I not receive an acknowledgement from in 2 seconds, I have to know in advance what those 100 devices are. So suddenly there's a lot of configuration information that each device has to have about the rest of the network. And in the event that something doesn't go perfectly, maybe my device has to start resending messages, and very quickly 2 problems arise in the design. We get horrible complexity with very tightly coupled nodes, because every node knows everything about every other node in the network, so it can do things like track acknowledgements. And you get very, very poor scalability, because again, as soon as something starts to go wrong, which it will, because wireless communication is unreliable unless you do things at a higher level in your protocol stack, you can very quickly generate a storm of messages. There's a really good Internet RFC, whose number I can never remember. I need to write this down one day. But I think it's called IP Group Multicast. It's got nothing to do with Bluetooth, of course, but I remember reading it, and it had a really good explanation of all the problems of dealing with communication where multicast messaging is involved and what happens when you try and respond to problems, the kind of thing that I'm hinting at now. So in actual fact, in a Bluetooth mesh network, the norm is to use unacknowledged messages, and we do other things to deal with reliability. So there you go, bit of a picture there of state changing in response to message being sent. Now, Bluetooth Mesh has an addressing scheme. So every device has a unicast address that's a unique 16-bit identifier for that device in the network. It's not quite the device, it's something else. We'll come on to that in a moment, but it'll do for now. More importantly, though, there are two ways of addressing collections of devices. We have group addresses and virtual addresses. The difference doesn't matter at the moment. What's important is that they are both concerned with addressing collections of devices. That kind of collection or set membership, though, is not known to any of the devices in the network at all. It all operates on a publish and subscribe mechanism. So on slide here on the screen, I have some light switches showing, and I've got a number of lights at the bottom. Lights and switches are great examples because we all understand them and know what they are. When I set up my network, when I install my devices, I go through a procedure called provisioning and configuration. Provisioning is a security procedure which makes the device part of my network. I'll talk a little more about security later on. And configuration is, as you'd expect, to do with configuring things. And one of the things I'm going to do with my light switches is I'm going to tell them the network address, a group address that they should publish messages to. And publishing means transmitting. So when I press a button on one of those light switches, it will transmit a message addressed to the address I've configured it with, but it will have no knowledge at all of the devices that will respond to it, because that's the other side of the equation. That's subscribing. Each of the lights I install in that room, I'm going to configure to subscribe to the address that my light switches are publishing to. And so subscribing just means be interested in and respond to messages with that address. That's all it means. So the lights at the bottom know nothing about the switches that control them, and the switches know nothing about the lights that they control. And the good thing here is that we don't have lots of hard-coded, almost hard-coded information about the network membership in the individual devices. So they're loosely coupled, which means I can make all sorts of changes, add more lights, add more switches, take things away, and it doesn't break my network. I don't have to reconfigure the whole thing. There are not lots of tables everywhere defining the membership of the network. So publish and subscribe is an important concept here. Devices that are part of my network are called nodes, okay? And they have a kind of hierarchical composition. If you're an embedded software engineer, you'll need to know this stuff. It'll be less visible to you as a smartphone engineer, developer, but nevertheless important. So a node is, let's say, a physical device. Some nodes have multiple individually or independently controllable parts, and we call those parts elements. So all nodes have one or more elements, and an element is the thing that has a unicast address. Now, sitting inside elements are things called models, and you should think of these as fairly granular software components that comply with a standard. All the models are defined in a Bluetooth Mesh models specification, and they define the way that a product should behave with respect to a certain set of operations. And I'll give you some examples in a moment. But what a product can do in a mesh network is a consequence of the particular models that have been implemented in it. And it's inside models that we have state values. And of course, models also bring with them particular associated message types, because it's the messages that act upon the states that a model has. So these are important concepts. So here's an example. Simplest possible message type is concerned with switching things on and off. And the model, or the two models concerned, are the generic on-off client model and the generic on-off server model. So yes, we have clients and servers. The difference between the two is that servers have state, whereas clients do not. Clients just generate and receive messages. Servers are the ones that actually store state, and that state reflects the physical state that a device is in and controls it. So change the on-off state of a light and it will come on or switch off, one of the two. Now, again, it's all about standards. So we have a number of specifications covering quite a big list of models now. We have a collection we call the generics. And this is one example, and they're generic for obvious reasons. Switching things on and off is not the sort of purview of a specific product type. All manner of devices can be switched on or off, and we have a big list of generic models that give some very, very common and generally applicable behaviors that you can exercise in your network, turning things up and down, for example. We have a big list of stuff to do with lighting. Lighting is an important area in commercial and residential buildings, of course, and lighting is remarkably complicated. You'd be surprised how much there is to the world of lighting, but that's reflected somewhat in the models defined for that world. And we have models to do with sensors, to do with what we call scenes, that's automation, and to do with time. You can schedule things as well. So big list of standard models, and what a product device type does is a consequence of the models that are implemented in code inside it. So here's an example. I've got an LED strip that has 3 individual LEDs in it. The node is the lighting unit as a whole, and each of those LEDs is individually and independently controllable. So each of those is an element. And it's the lighting company product designer that makes these decisions, that decides that each light should be individually controllable. And consequently, because they're using Bluetooth mesh, each will be an element, each will have an individual address, which you can see on the slide there. And then we'll select the product designer will select the Bluetooth mesh models that need to be implemented in its code to give it the behaviors that we want the product to have. So we've got the generic on-off server here because we want to be able to switch them on or off, and something called the light lightness server, which allows us effectively to turn the brightness of the light up or down. Now we also have the generic level server model, which lets you turn things up and down. But lighting works in a non-linear way to do with the way human perception works. And I think it's a logarithmic scale that actually gets used to deliver changes in brightness that make sense to the human brain. And inside each of those models, you can see examples of the state data items that they each have. Very briefly, let me talk about security. It's a big subject, of course. I have some bullet points here and some more information on the next slide. First of all, you'll probably be aware, if you've worked with Bluetooth Low Energy, with GATT and GATT Bluetooth peripherals, those kinds of things. In that world, security is actually optional. We don't mandate security in that use of Bluetooth. The point being that we don't know anything about the security requirements a manufacturer might have for their particular product, used by their particular types of users in whatever circumstances or conditions. So Bluetooth Low Energy for connectable devices gives you a toolbox of security capabilities, but it's up to the manufacturer to select from that toolbox those security features they think they need for their product, having done their own security assessment. That's how it works. And some products, it's a very conscious decision to give them no security at all because they have to be publicly usable, for example. Bluetooth mesh, that's not the case. Bluetooth mesh mandates security, so it's absolutely mandatory. Couldn't have the situation where one device in your network weakened the security of the whole network for everybody, so it's all mandatory. All messages are encrypted and authenticated using AES-CCM. 2 sort of levels of security. There's network layer security and application layer security. So at the network layer, you can define networks and subnets, each of which uses its own security key for encrypting relevant parts of the PDUs that get transmitted. But you can also define what we call applications. So this is entirely up to the network designer, but lighting might be one network application. Air conditioning might be another application. And you can issue separate application keys for each of those groups. When you configure your products, your nodes to be part of your network, you tell them which application they're a part of and give them corresponding security keys. And the reason for separating application and network layer security is it means that any type of device can be a relay because that's a network layer operation, and it can decrypt the networking related parts of PDUs, but it can't necessarily see all the application layer stuff if it's not part of that application. So a light, which is part of the lighting application, can act as a relay for the temperature control subsystem in the building, but without seeing any of the content of the temperature related data, because it doesn't have the right application key. So that separation is quite powerful. You can achieve something called area isolation. So you can issue different network keys, create subnets for different physical areas. If you think about hotel rooms, this is the way you'd approach that. You'd have different subnets for each hotel room, and when you check in, your smartphone probably would be issued with some keys that allow you to use the hotel's application to control all of the smart devices in your hotel room, and not the room next door to yours, because that would be, well, that would be inconvenient for people, wouldn't it? So area isolation kind of cryptographically puts a boundary around different physical areas. There's an obfuscation process, because one of the threats is something called network pattern analysis, where a kind of malicious observer can watch what's happening in a network at a high level, start to deduce patterns of behavior, and from that start to infer maybe the behavior of humans and their devices. So all messages are also obfuscated. And there are some standard attacks like replay attacks and trash can attacks, where you pull a discarded device from the trash and you extract its keys and you try and use those in some form of attack. We've got protection from those built in. Replay attacks, if you're not familiar with that one, is simply recording a message in the network. You don't need to decrypt it, you just retransmit it in the hope that you will bring about an unintended or unwanted change to some device. And again, we stop that happening through a series of sequence numbers that every message has. Devices themselves are not part of your network until provisioned. And again, provisioning is a process. It involves a smartphone application, and amongst other things, it gives the devices that you want to introduce to your network a series of security keys. And it's possession of those keys that makes the device part of the network and able to communicate with its neighbors. The provisioning process itself uses elliptic curve cryptography. It's not completely dissimilar to pairing, except that it's not pairing. It's a little different. So here's a picture of some keys. So there can be many keys in a Bluetooth mesh network depending on the complexity of the network design, but there's three important types of key. So the network key is used to secure network layer related fields in a PDU, and possession of a particular network key means this node is a member of the corresponding network. Application keys, hopefully I've already kind of described. We use those to separate application security from network security, and you can have multiple application keys, and they actually get bound to individual models in products. In nodes, device keys are for securing direct communication with one specific device. So every device has a device key, every node has a device key, and it's different on every device in your network. Now, the only time we use device keys is when provisioning and configuring an individual device one-on-one. Okay, so that's when that key gets used to secure the link. The rest of the time, it's all about the network key and the application key. So, one of the things we want to talk about today is creating Android applications which can talk somehow to the network. And this is done via a special network device type called a proxy, which I'm going to tell you more about in a moment. The question arises, if we need all these keys to be able to securely communicate with nodes in the network, then what about smartphone applications? And the same rules apply. Your smartphone application essentially has to be part of the Bluetooth mesh network. In other words, it needs to have network keys and application keys, or at least one of each of those two types. How does your application get them? We don't define a way of doing this specifically for smartphone applications. We define procedures and protocols. So if you can implement those procedures and protocols within your smartphone, go for it. We include some ways of doing this out of band. One of them is probably going to be suitable for you. If not, I wrote a whole blog post on it, and I've just thrown it into this presentation for your information, a whole discussion on how you would provision mesh applications involving things like smartphones. I think I actually focused largely on web applications in that blog post, but I just thought I'd mention it. So let's now reflect on what you have on Android devices, which from the beginning in the stack that I showed you involves things called GAP, GATT, and ATT. So these are parts of the Bluetooth Low Energy stack that sit in the host, and these are things that you do have on an Android device. I just want to make sure everyone has the basic concepts around this before we move on. I imagine some of you already do. So a remote device, a Bluetooth peripheral of some sort, has inside it something called an attribute table. And the attribute table is a list of data items of which there are sort of three fundamental types that form a hierarchical relationship between them. You have services at the top. These are like grouping mechanisms for characteristics, which are really just data items. They have a type and they have a value, and there's a list of operations that they support, like the ability to read a characteristics value or change it by writing to it, or enabling something called notifications, where values of that data item, that characteristic, whenever they change, get transmitted to the remote device automatically, or maybe that's done on a timer basis every second or something. And at the bottom level of the hierarchy, we have descriptors, which are completely optional. They're associated with characteristics. So a characteristic can have 0 or more descriptors attached to it. They contain metadata, information on how to display a characteristic value, for example, or configuration flags, such as the ability to switch on characteristic value notifications, one of the operations that some characteristics supports. So services, characteristics, and descriptors, these are things that you work with in an Android application. Your application flow will typically go through these stages. A remote device will be doing something called advertising. This is broadcasting some information about the remote device so it can be discovered. You will do some scanning from your application and then connect to a selected device. Typically, you'll scan, discover some devices that look like they're appropriate for your application. The user will then select one of the discovered applications from your screen, and you'll connect to the remote device. Having connected, you initiate something called service discovery. Service discovery really is just you saying to the remote device, please tell me more about what you've got in your attribute table, and you'll discover the services, characteristics, and descriptors that it contains. And they're all identified by a UUID, so you'll be able to recognize the type of each of those things that you discover and then decide how to proceed. From there, it basically tells you more about what the device is and what it can do. Once you've done that, and we have a connection with the remote device and we know enough about what's in its attribute table, you can then proceed to interact with entries in the attribute table, typically characteristics, which will read, write, and enable and consume notifications if they're supported. That's the kind of thing that you generally do. Let's talk about mesh next, though. Because Bluetooth mesh, you do not have. Sorry, let's talk about Android and those Bluetooth concepts. My apologies. So you have quite a nice set of classes that constitute the Bluetooth Low Energy API. In Android, I've listed the key ones on screen here. For the scanning and connecting stage, you've got Bluetooth LE scanner at the top. That's the main one for initiating scanning. Scanning is the process for listening to and collecting advertising packets from devices that are advertising, but you can configure it to filter out packets that are not going to be of any interest to you and make sure that only ones that are apparently being produced by candidate devices to connect to are coming into your application, so you can choose appropriate devices only and not bore your user with all sorts of devices that are out there advertising that are completely irrelevant. The end of the process, though, is that you have a Bluetooth device object that's been selected by the user and you're going to connect to it. Once you're connected in a connected state, Bluetooth GATT is the most important class. It's kind of like a facade API that lets you invoke all sorts of Bluetooth operations, such as reading and writing and notifying and so on. They're all asynchronous. There's a kind of callback pattern with all of this stuff. And there are classes that represent services, characteristics, and descriptors per the slide I showed you with the sort of hierarchical thing. And as you can see, they even have the word GATT in the class name because it comes directly from part of the Bluetooth Low Energy stack that we saw. Now, here's the magic part. You don't have a mesh protocol stack on your Android devices. Bluetooth mesh networks, generally speaking, don't know about the kind of stuff you can do from an Android device, except in one respect, one special respect. I mentioned very early on that devices can be given one or more special networking roles, or none of them. Most devices will not have any special role to play. Some of them, though, will have special roles. One of them you've already met, and that was the relay. So we're going to enable relaying in some of our devices so we get multi-hop and multi-path message propagation across the network. But there's also a proxy node, and the proxy node is key to you as Android developers because it supports both Bluetooth Low Energy GAP, GATT, and ATT, and it supports Bluetooth Mesh. So it acts as a kind of translation device that can mediate and kind of translate between these two worlds. And it's the proxy node that you will be using should you write a Bluetooth Mesh Android application. There you go. So let's look at a bit of code and then sort of drill down on exactly how you'd use a proxy. So the first thing you're going to need to do is discover a proxy node. Proxy nodes are going to be advertising. So the first job you have is to scan for proxy nodes so you can find one and then connect to it. To do this, there's an abstract class called scan callback. You have to implement it. There are some methods you can override, one of which is called onScanResult. So this is where essentially advertising packets plus some associated data such as the signal strength, they get passed to your application by callbacks to this method. You'll initiate scanning using the Bluetooth LE scanner class, which you're going to kind of configure to have some filters using the scan filter class. Here you can see that I'm basically saying I'm only interested in advertising packets that include the service UUID for something called the mesh proxy service, because proxy nodes advertise a particular Bluetooth mesh service using its UUID. And since I'm looking for mesh proxy nodes, having that in my filter criteria seems to be like a good thing to do. And then there's some settings you can configure scanning to use to do with things like how quickly things are discovered versus how much power is used. And then you kick scanning off. You're going to have some kind of timer which will stop scanning maybe after a few seconds, and you'll present the results to the user. Once we've selected our proxy and connected to it, you can now start working with that proxy node using standard characteristic write operations and notification handling, because you inject messages into the mesh network in a special way, which I'll come on to, by writing to a characteristic value, and you receive messages as notifications. So at this stage of the game, the code you're seeing is no different to any other Bluetooth Low Energy code you might have written for an Android device. The key to this stuff, though, is what's in those write values. You're going to use something called the mesh proxy protocol. And the mesh proxy protocol lets you essentially put mesh network PDUs, of which there are various types, inside characteristic values. And it looks like this. On the screen here, we've got a mesh network. There's a proxy node I've represented as a big rectangle, and there's an Android application at the top. Now, the proxy node is a full mesh node, but it also runs GATT, GAP, and ATT, and it has a Bluetooth service called the mesh proxy service, which contains two characteristics: mesh proxy data in and mesh proxy data out. And these are your kind of the mechanism you use for getting messages in and out of the mesh network. So obviously you can see the kind of both variants of the protocol stack are supported by these special nodes, the proxy nodes. So to inject messages, you use the proxy protocol, writing to the mesh proxy data in characteristic, and as I said, notifications are the mechanism for delivering mesh messages to your application. Now, what exactly do we write in those characteristic values? All we ever write in reality are byte arrays, but what is it that's in those byte arrays? So proxy protocol PDUs have a very high level structure. At the very beginning, there's a bit that says whether or not what you're writing is the full proxy PDU or just part of it, because you can have ones that are too long for an individual write operation. You can split them up or segment them, and the remote device will reassemble those parts for you. There are several types of Bluetooth mesh PDU. There are network PDUs, beacons, configuration PDUs, and provision PDUs. You're going to be interested in network PDUs, and the type fields indicates what it is that we're sending inside the data part of the proxy protocol PDU. PDU is protocol data unit, if you're unfamiliar with that term, by the way. So here really is the main part of the work that you have to do, apart from developing user interfaces and discovering and connecting to proxy nodes, which is kind of standard stuff that you might do with any Bluetooth related Android application. You have to formulate this PDU. So let's look more closely at the payload, the data part. So in there, it splits into 3 parts which correspond to different layers or groups of layers of the mesh protocol stack, if you remember that from earlier on in the talk. We've got a network layer part, stuff to do with the transport layers, and stuff to do with the access layer, which is the top kind of messaging application layer. The network part contains things like source and destination addresses. The transport part has more to do with segmentation and reassembly, but this is segmentation and reassembly of the mesh PDU rather than the proxy PDU. Now, what we're doing here is a form of encapsulation or tunneling, really. We've got protocols inside protocols. And the access layer at the end contains your actual message with an opcode that identifies its type and some fields that follow it, and they're all defined in the spec. You have to secure your PDU, because don't forget, security is mandatory. So you're going to obfuscate the network parts using AES. You're going to use AES CCM to encrypt and authenticate the transport layer parts of your PDU using the network key. And don't forget, you have the network key because your application has been given it somehow, probably out of band. And the access layer parts of the proxy PDU, you're going to do the same thing, AES CCM, but you're going to use a different key. This is where the application key comes in. So you have some work to do, but none of it's difficult, to be honest. 3 things really that you're going to be doing and that you need to formulate a proxy PDU properly. You need to be able to work with byte arrays. So I use byte array output stream to slowly but surely kind of build up the different fields in a PDU. That's really basic stuff, very easy. You need a crypto library. As far as I could tell, by default, Android doesn't support all of the crypto functions that you're going to need. So I use something called the Spongy Castle, strangely named library, brought to you by those lovely people who brought us the Bouncy Castle cryptography library all those years ago. So they've been around for a really long time. And you need to do some large integer arithmetic for some of the crypto functions, and we're good where that's concerned. We already have the big integer class which does the job. So I'm going to show you some code. I'm not going to labor this because we're quite short of time, I think, now anyway, and I don't really want to send you to sleep, but I'll just give you a glimpse of what code looks like. And by the way, this code is available for you to download. I'll point you at some resources later on, so you can go grab a kind of full working mesh proxy application for Android, of which this is the code. If I can switch to the right screen. Here we go. So ignoring UI stuff, I've got a number of classes here, including this one called Bluetooth Mesh, which is a brilliantly imaginative name for my class. You can also see I've got a crypto class with all the crypto functions in it. Just to give you a sense of what's involved, and don't forget, hey, I've written this code. You probably save yourself some effort by reusing at least some of it. One of the things my application does is lets me switch things on or off by sending generic on-off set unacknowledged messages. That's the message type. So here's my function. The UI calls this, and I check that I'm actually in a connection with the proxy first of all. I create a byte array output stream. And then the first thing I'm concerned with is the access layer. And the access layer is where I specify the type of message that I'm sending. They all have unique 16-bit identifiers. This one has an opcode value of 0x8203. That's generic on-off set unacknowledged. So I populate my byte array output stream with that data, and then I kind of move on to deriving the fields relating to the lower layers of stack, which hopefully I can switch to here. Yeah. We're kind of doing more of the same. So I've got functions, or methods rather, which derive individual fields or groups of fields from the different layers of the stack. And I'm kind of appending them to my byte array output stream as I go. Now, somewhere amongst all of this stuff, you can see it's not a huge amount of code that's involved here. I'm going to do some cryptography as well. If we switch to the crypto class, you'll see that I've got something called K2 here, which is not the mountain, it's something else. You're going to write stuff like this with the spec open. Here's the mesh profile specification as it's known. So the security functions are all defined in here. K2 is one of the important functions. We've got K1 through to K4. And you can see that it defines the arguments to that function and how they're used. Ultimately, K2 takes two parameters, N and P, and returns various parts of the encrypted payload. And if you look at the signature of my K2 function, I've got N and P. There you go. Didn't do anything too exciting there. So a bit of code there involved in securing, in this case, the sort of network layer fields in my PDU. PDUs look like this, and this is actually a screenshot from one of our educational resources that you can download from Bluetooth.com, where you use a Raspberry Pi as your proxy node. It doesn't do anything. All it does is decodes proxy PDUs as they arrive and dumps them to the console, nicely formatted and color-coded so you can see what's going on. It's not actually part of a Bluetooth mesh network. It's just a kind of educational device, but this screenshot, I think, helps you understand the kind of breakdown of a PDU rather than just looking at a hex byte array dump. So I'll very quickly now show you a demonstration. This is not going to be live. This is a video I prepared earlier. You may have seen this on my last talk. So what I've got here on screen is, well, it says it there, doesn't it? A kind of live screen capture of one of my Android devices, which has an application on it called Mesh Controller that I wrote. That's the one we were just looking at the code for. And I've got these 16 independent microcontroller-based devices, each of which has Bluetooth mesh and code that implements the models. Don't forget, the models are essentially the application layer in the world of Bluetooth mesh. So I wrote the models, and the code running on these devices is from something called Zephyr. So Zephyr is an open source embedded SDK, a framework, a real-time operating system from the Linux Foundation, actually, and it's got good support for Bluetooth mesh, so I tend to use that quite a lot. I'm just picking one up here to show you what's underneath it. It's attached by Velcro to a bit of card, because I'm such an engineer. Big battery in there, circuit board, tiny little chip and antenna. So I've implemented the generic on-off server model and the light HSL server model. HSL, by the way, stands for hue, saturation, and lightness, and it's a way of representing color. And so each of these devices has an LED which is colored, and one of the things I wanted to do is change the color. Now, I think there's something I've forgotten to tell you here. Let me just stop there for a moment. What I did there was discover the proxy node. One of them is acting as a proxy, scanned for it, discovered, and I'm about to connect to it. One thing I should mention is that every single one of these 16 nodes has subscribed. Remember the publish and subscribe mechanism that we use? Each one is subscribed to 3 addresses, 3 group addresses. They've all subscribed to an address which means all nodes in the network, and they've each subscribed to an address which represents the column that they're in, because I've arranged mine in a grid, and also the row that they're in. So let's continue the video. I'm going to connect now. Oh, there you go. So like I just said, so my UI lets me select addresses. So at the top here, this is meant to represent the grid, and by touching the big square, that selects the all devices address, which here is hex C001. And then I can select an operation, and hey presto, I hit the on button and they all came on. If I change to a different address, the second row, same operation though, the same message type was sent with the same value of 1, meaning switch on, but because I sent it to address C012, only those devices which subscribe to that address, which are in that row, responded. So if we continue, changed to column C3, different addresses you can see at the top there, and again, only that column responds. Back to all, switch them all off by sending a generic on-off set, which has a value of 0, meaning switch off. Switch them all on again, and I'm going to change the colors now. So I hit the red icon, and that sends a light HSL set unacknowledged message with a kind of set of parameters that selects the color red. And so on. So I'm just exercising I'm selecting different addresses. I'm sending messages to those addresses of a given type. Those devices that have subscribed to that address and implement the right models are responding, as you can see, all being done by an Android application which is connected to a proxy node, which acts as a kind of go-between. So we're kind of at the end. I just want to point you at some resources. So if you want to know more and maybe get some hands-on practice, which is always the best way to learn, if you go to our website, so bluetooth.com is the place to be. There are a number of resources that are worth reading. But you can skip these if you don't want to do any reading. We've got a paper called the Bluetooth Mesh Networking Introduction for Developers. It's actually only about 8 pages, and it summarizes all of the key points about mesh when you're a complete beginner to the subject. It's quite an easy read, to be honest. They've made it look like 20-odd pages by adding lots of pictures. There's a technical overview paper that takes you on a kind of guided tour of all the standard mesh models. Those are those application layer kind of standard product behavior components. Excuse me whilst I have a little drink there. And then we've got things we call study guides. And study guides are educational resources aimed specifically at developers. They always have some hands-on kind of project work in them, often a lot, actually. I tend to learn best by doing, and I think a lot of developers feel the same. So the first one, the Introduction to Bluetooth Mesh Network, is quite extensive, and you will get to build pretty much the demo that I just showed you. You'll need some hardware, some devices. It tells you what you need, and you'll get to do some coding using the Zephyr SDK. We also have one specifically on the mesh proxy function, and that takes you through what's involved in creating exactly the kind of application we've been talking about, both for smartphones and for the web. So using an API called Web Bluetooth. There you go, and that's application we started looking at the code for is sitting right there. I'm going to just show you where that is, just in case you find our website hard to follow, or at least I'm going to try. Let's try going here. Let's go here. Yeah, so if you go to bluetooth.com, let's go to the home page so you know what it looks like. That was the blog post I was talking about. If you click on resources, we've got all sorts of stuff in here. Study guides are those educational resources for developers. Papers are self-explanatory. If you click on study guides, you get a whole series of things. You can filter on keywords and tags, but you'll see the kind of things that are in there. There's a whole thing on security, everything you ever wanted to know about security in the Bluetooth LE security study guide. There's the mesh proxy guide. And right next to it is the one for mesh development and other things as well. So pretty much everything you ever wanted to know should be available in there. And if I can find my way back to my presentation slides, that, my friends, is all I wanted to cover with you today. Hope you're all still out there. Thank you so much if you are for listening. Really appreciate you showing up today. And I think we're going to have some time for Q&A now using the Slider application. So I'm going to switch to Slider so I can see what's going on. At least I'm going to try. Probably that one, I think. Yes, it is.
Thank you, Martin. Martin will be taking question in 3 seconds. And just want to say thank you once again to our sponsor, Bluetooth, and let you know that our next webinar will be on Tuesday, 16 June. at 3 p.m. Hope to see you there. Back to you, Martin, for the question.
Okay.
Thank you.
Yeah, thanks so much, everyone. So I'm just going to read through the questions on screen and give you my answers where I can. Starting at the top from Mr. or Mrs. Anonymous, is a citywide Bluetooth network possible? Aside from low data rates, is such a large-scale Bluetooth-based peer-to-peer network feasible? So I am, of course, as an engineer, I am pedantic. So it's not really a peer-to-peer network. So this is mesh networking. But is a citywide Bluetooth mesh network possible? It depends how big the city is, obviously. Cities tend to be many, many miles across. Small cities, maybe. It's not particularly what was envisaged. If you imagine right now, so Bluetooth Low Energy, which is the the communications technology under Bluetooth Mesh,